Hello, everybody. Welcome to the ICANN use talk. Today, first, please let me have a self-introduction. Today the use talk will be monitored by me. I'm Jingdong Xu from University of Macau. I'm a professor at the Department of Electromechanical Engineering and Faculty of Science and Technology. My research about the robotic automation, micro nano system, and robotics. Okay, before the start of today's use talk, because this is all of the speakers are from our University of Macau, so I will give you a brief introduction about the University of Macau. Our university. The rank of the university is showing this figure. Okay, we can see in both the PhD and the QS, we have a better and better rank. Okay, in the world, and we have 14 research fields among the top one in the ESI or Web of Science. And talking about the robotics, okay, because today's talk is about the flagship robotics. All of the speakers belong to the Center for AI and Robotics. We have a new master program, the Master of Science, Robotics and Autonomous System, and we are recruiting a new master student for this program. Okay, this year is the first year. Okay, this is the speaker and also the panelist of this use talk. First, I'd like to give a brief introduction of the speakers. The first speaker is Professor Aiman Li. Professor Li, I'd like to give a brief introduction. Professor Li is currently an assistant professor in our department. She pursued the PhD degree in engineering from the University of Cambridge in 2022 and completed her master and undergraduate study with a first-class honor from the Imperial College London. Her research interest currently focuses on the soft material fabrication, bio-inspired soft material, and soft robotics. Dr. Li had published a series of peer-reviewed articles in professional scientific journals, including Nature Electronics, Nature Communication, Advanced Material, and Advanced Functional Material. Okay, first, let's welcome Professor Li.
Hi, Lee, you mute yourself. Please unmute yourself.
So can you hear me now?
Yeah. Please go ahead.
Okay, yeah. So my name is so thank you so much for the introduction. So my name is Ying Jiang. So I'm currently an assistant professor at the University of Macau. So today's my topics is about 3D printing of soft materials, embedded shapeabilities using supportive path matchings and applications to human cochlear modeling. So since today's topics is about flexible materials, I would like to give some background introductions about soft materials. So soft materials are a class of materials that can be deformed easily with external forces. So there are many different types of soft materials existing, such as hydrogels that contain a huge amount of water, foam which is porous and lightweight, elastomer that has excellent stretchabilities, colloid polymers, and liquid crystal elastomer. They all belong to the classifications of soft materials. And so I think why soft materials is so interesting is because we can actually tune the mechanical properties of soft materials to make it match the mechanical properties of human soft tissue. So because of this reason, many soft materials have a very promising potentials in bio or human machine related application. And so so depending on the types of soft materials could be very soft, have tissue-like wetness, they could be responsive to the external environment, they could be recyclables, antibacterials, and also have some biocompatibilities or behavior. And so, we because of these very unique properties of soft materials, there has been soft materials has been used in many different types of application, and then there has been rising demand for soft materials in modern technologies such as flexible devices, soft robotics, wearables, and bioelectronics implant, etc. So in our research group, we are particularly interested in how to structure soft materials, how to utilize the shape of the materials to enable soft materials with unique and advanced functionalities. Materials always require shape for functionalities. For example, the spiral shape of the cochlea are important for hearings and the auditory sensation. And then in a recent study, it was found that the surface of a plant has the ability to transport a specific liquid unidirectionally. So in our lab, we conducted research on various 3D printing technologies. And the reason why we are interested in 3D printing is because it enables the rapid transformation from design to product. It also allows fabrication of complex shapes, enables tailor-both properties, and also as well as enables customization. So we developed different types of 3D printers in our lab. For example, digital light processing, which utilize light to 3D print photocurable polymer. Yeah, so the light is shine on a photocurable polymer layer by layer to form a 3D shape. And then we are also interested in direct ink writing, which utilize an extrusion mechanism to extrude the soft materials out into 3D shapes. And this 3D printing method has the advantages of a wide compatibilities of different types of materials. This method can be used to print very viscous materials. So after printing, we use, depending on the types of the materials, we use different types of cross-linking method to cross-link the materials. And we also conducted research on embedded 3D printing, which involve extrusion printing of soft materials in a supportive bath. And so we will further talk about these technologies in today's talk. Yeah, so this is the extrusion ink writing. So the ink is extruded and then printed into 3D shape according to the user or CAD files. So in the first work today, I would like to talk about sustainable 3D printing of photonic structures. And so the reason why we would like to develop a sustainable 3D printing materials is that 3D printing is a rapidly expanding technologies, and then there has been growing increasing environmental concern about the 3D printing materials. The current 3D printing materials usually are either petroleum-based or have some kind of environmental or degradability issue. And so because there is a growing need of materials for 3D printing, we are interested in developing sustainable 3D printing materials based on a materials called hydroxypropyl cellulose. So the reason why we are interested in hydroxypropyl cellulose, these materials, is because it is a renewable, sustainable resource. It is also a FDA-approved food additive, so it is a very safe materials. And it is also a very economical and it is also a biodegradable materials. And so more interestingly, these materials can exhibit a very brilliant structural color at a specific range of concentration. And this kind of color is a long-fading structural color. So therefore, we would like to utilize these materials to develop a sustainable 3D printing ink that can be utilized to print photonic structures. So to give more information about the structural color of hydroxyl propyl cellulose, so at a specific concentrations of hydroxyl propyl cellulose in a solution, this polymer will self-assembly into a helicoidal nanoarchitecture. And so because of the existence of these helicoidal nanoarchitectures, when light shine on this polymer, there will be a specific wavelength of the light will be reflected from the polymer solutions. So therefore, we can tune the structural color, tune the color by changing the concentrations and the temperatures of the materials. And so this kind of structural color is also very similar to what we observe in many biological creatures. So many biological creatures, such as the beetles and the butterfly, has a very beautiful structural color on it. Is due to the is because of this kind of structural color, because there is some kind of structures on the surface of the biological creatures. So therefore, this kind of creations can reflect a specific wavelength of light, causing this very brilliant color on this body. One major challenge to convert these materials into 3D printing materials is that we need to solidify the materials. At the same time, we need to maintain the helicoidal nanoarchitectures. So in order to have this kind of structural color, we need to dissolve a huge amount of polymer or a high concentrations of polymer in a solution. And so in order to cross-link it, when we use some cross-linking method to cross-link to solidify the materials, most of the time the helicoidal nanoarchitectures will be destroyed. So therefore, the color of the materials will be disappeared. And so to address this problem, we developed a methyl acrylate functionalized hydroxyl propyl cellulose materials. And these materials is photopolymerizable. And by combining extrusion printing with an in situ UV cross-linking method, we are able to do direct ink writing of volumetric object with structural color. So with the in situ UV cross-linking method, the materials can be quickly solidified, and then the helicoidal nanoarchitectures can be locked due by the UV cross-linking mechanism after we extrude the materials out. And so in our work here, we have actually optimized the cross-linking rate to optimize the color intensity. And so by changing the concentrations of the HPC ink, we can adjust the color of the object of the printing. And then from here, you can see that we are able to achieve objects with different types of structural color using one single feedstock by varying the temperatures during cross-linking. So these materials, these HPC print are printed by one single materials. And by changing the temperatures during printing, we can achieve different types of color in one single object, or in these objects. In the next part of this talk today, I would like to talk about the fabrications of hydrogels materials. And so the previous method utilized an in situ UV cross-linking method to solidify the materials. But not all the materials, not all the hydrogels or other polymers are photocurables. And so hydrogels are particularly difficult to fabricate into 3D shape is because these materials are very soft and they have low stiffness, poor toughness, and they are very easy to deform. So these factors actually add a lot of complexity to the fabrications process. The videos here show that if we utilize transition extrusions 3D printing to print the soft materials, most of the time the materials will spread due to the lack of the mechanical properties. So basically, the shape is very difficult to form the shape of the hydrogels using traditional extrusion-based 3D printing. So to tackle this issue, there has been work developing a method called embedded 3D printing. So in this method, the ink is printed inside a supportive bath in a yield-stress supportive bath. So the yield-stress properties of the supportive bath allow the needles to move through the bath easily. And then the bath also have suitable rheological properties that can support the printed ink. It also allows a longer cross-linking time, allow the structures to be cross-linked inside the bath. We can also add some cross-linker in the bath to facilitate the cross-linking process. So this method can allow freeform printing. So with this method, we are able to create different types of complicated freeform 3D construct. For example, this Verso-like construct, we can print this with embedded 3D printing using with ultra soft hydrogels materials. We can also do different types of freeform construct that is previously cannot be achieved by the traditional extrusions 3D printing. So the concept of embedded 3D printing seems very simple, but the actual process is quite complicated because actually there are two phases involved in this embedded 3D printing. So therefore, there are many factors happening at the ink and the bath interface that could affect the shapeabilities. And so during printing, there could be quite fast recirculating rate and sagging happens if the rheological properties of the ink and the bath are not matching. And then there also could be molecular diffusions. So small molecules could diffuse between the ink and the bath during printing and then after printing. And this will sacrifice the print resolution. And osmosis, there could be water diffusions to the ink phase and the electrostatic interactions as well as interfacial tension. So these factors will affect the embedded shapeabilities. And so this will cause poor embedded shapeabilities. And this means that the ink may not be able to cross-link inside the bath, and there could be shape deviation. So a good embedded shapeabilities means that the shape can be retained within the supportive bath with the distinct boundary, and then the ink can be successfully cross-linked inside the bath. And to achieve a good embedded shapeabilities, matching the properties of the ink and the bath is very important for the success of embedded 3D printing. So although there has been many different types of supportive bath developed in literature, such as gelatin slurry, carbopool, aqueous fluid gel, and oil-based supportive bath, these studies mostly focus on high molecular weight hydrogels. So the methodologies for choosing the suitable supportive bath for different types of hydrogels has not yet been established. And so hydrogels, there is a large families of hydrogels materials. So it is very important there is a guideline for choosing different types of supportive bath for different types of hydrogels materials. So in our recent work, we have systematically investigated the embedded shapeabilities of different hydrogels materials using the representative supportive bath in literature. And the ink we tested here are the pH-responsive hydrogels, thermal-responsive hydrogels, anionic hydrogels, cationic hydrogels, photopolymerizable hydrogel, and the small monomeric hydrogels forming ink. So the reason why we choose this ink for testing is because these materials mostly cover the materials utilized in biomedical research and the soft robotics research. And from our result, we find that there are two key instabilities affecting the embedded shapeabilities. And the first one is the molecular species transportation. The second one is the charge-driven interactions. And based on our result, we have established a guideline for fabricating different types of hydrogels forming ink. And so we hope that this guideline can provide some information for the user to efficiently find out a supportive bar for the hydrogels forming materials. And then this guideline can also widen the spectrums of hydrogels that can be constructed with embedded 3D printing. So the current work allows us to print hydrogels with good hydrogels of soft materials with good shapeabilities. But these structures usually lack shape-induced functionalities. In the following work, I will talk about how we utilize the embedded 3D printing to produce a construct, and then these constructs have the shape-induced functionalities and properties. So this work is about 3D printing neural network co-modeling of the current spread in cochlear implant user. And so it is about the development of a biomimetic cochlear model that can represent the electroanatomical properties of human cochlea. So before we move on, so I would like to give some background information about our human cochlea and the cochlear implant. So the cochlear implant consists of an electrode array that have many electrodes on it. So it can be 16 to 22 electrodes on this electrode array. This electrode array is surgically inserted in a patient's cochlea. And so depending on the frequency of the sound the patients receive, a specific electrodes on the electrodes array will be activated. And so this will stimulate a specific portion of the auditory nerve. So this kind of working principle is trying to restore the holotopic organization of human cochlea, so where different frequency of sound are processed at different locations along the cochlea. One major limitations of the current cochlear implants is the imprecise stimulation. So this is due to the fact that cochlea is filled with a conductive fluid called perilymph. So when we activate an electrode inside a conductive medium, the current will spread within this conductive environment. This will cause a larger portions of the auditory nerve being stimulated. And so because of this reason, the sound received by the cochlear implant user could be very different from the original music or the original sound. Yeah, so the current spread problems can be visualized by the electric field imaging profile. This electric field imaging profile is a clinical readout that shows the voltage distributions along the electrode array inside a patient's cochlea. These voltage distributions depends on the cochlear anatomies, cochlear resistivities, as well as the electrodes positions in the cochlea. So in order to improve the implant, in order to have further developments or further advancement of the implant, we artificial cochlear model are needed. Artificial cochlear model that can model the current spread problems are needed for the implant developments. So although there has been many testing models available for testing the cochlear implant, but the current testing models are deficient in modeling the current spread problems. For example, the animals model, so they cannot mimic the human cochlear electroanatomical features. So animals' cochlea have very different shape compared to our human cochlea. And then finite elements modeling cannot mimic the geometry guided positions of the electrodes, and the cadaverite models will have the ethical issue, and they also have poor availabilities and high cost issue. So because of this reason, this study combined embedded 3D printing and a neural network models to model the relationship between the electroanatomical features and EFI profile. So this can be used as an artificial and computational model to model the current spread problems. So this biomimetic cochlear models is produced using the embedded 3D printing method. In the first step, a sacrificial ink materials is printed inside a silicon matrix. So this step is for tuning the resistivity of the matrix after the fabrication. In the second step, a cochlear shape lumen is printed inside this interconnected network. And then after printing the cochlear shape lumen, we thermal cure the matrix. And then after the thermal curing, we remove the sacrificial materials and filled the microchannel network with saline such that the matrix could become conductive. So the resistivities or the conductivities of the matrix depending on the density of the interconnected microchannel network we print inside the matrix. And from the CT scan of our models, you can see the microchannel network. And inside this microchannel network, there is a cochlear shaped lumen, a biomimetic cochlear shaped lumen. And we can also insert the cochlear implant in it such that we can see the electrode positions inside this biomimetic cochlear. So by varying the density of the interconnected microchannel network in the matrix, we are able to achieve similar impedance properties compared to a human cadaveric cochlear. And then we can our human skull, the resistivities of our human skull actually vary a lot from patients to patients. So in order to capture these resistivities variations, we tuned the density of the interconnected microchannel network inside the matrix such that the resistivities can be mostly cover the resistivities of live human skull. And so the geometries of our human cochlear will vary from patients to patients as well. So therefore, we use 4 different geometrical descriptors to describe the cochlear shape. And then we produce samples with different geometry and different electrical properties to represent the human spectrums. And so after we produce the samples, we measure their corresponding EFI profile. And then we develop a neural network models to model the relationship between the cochlear electroanatomical features and the electric field imaging profile. So our models, our method, we call it 3PNN, which stands for 3D printing and neural network co-modeling. And then this method is validated with clinical data. And so this co-modeling approach can be utilized to predict the patient's EFI profile. It can be used to infer the patient's cochlear resistivities and geometries. It can also do on-demand printing of patient-specific models that can give similar clinical EFI profile. It can also be utilized to predict which cochlear features are more susceptible to the current spread. So in conclusions of this work, our research utilized embedded 3D printing to produce physical model that can reproduce the electrical and anatomical features of human cochlear. And so it is also able to capture the voltage distributions evoked by the cochlear implant. And then by combining neural network co-modeling, we obtain a 3PNN co-modeling approach. And then this approach, we think that it is an economical, ethical, and physical manipulation method, which can reduce the need for animals experiment. So we think that this concept can facilitate the physical modeling of bioelectronics implant. So just a slide to summarize our research interests. So my research group focused on sustainable soft materials fabrication technologies, soft materials mechanics, and bioinspirations approach to impart advanced properties to soft materials. So we hope that by tackling these challenges in this research area, we are able to advance soft materials in human-machine interface application as well as biotechnologies applications. If you are interested in our research group research, so we are also recruiting motivated students to join our team. So feel free to get in touch with me, and so we welcome all the inquiry. So to acknowledge our research, for acknowledgements, so I would like to say thank yous to all my collaborators, in particular my PhD supervisor Sherry, all my lab members, as well as the funding. So without the collaborator and lab members and the fundings, our research would not be possible. Yes. Yeah, so thank you. So I welcome all the questions in the later sections.
Okay, thank you, Professor Lei, for the exciting presentation. Okay. Okay. Okay, let's thank Professor Lei again. Okay, the next speaker is Dr. Zehao Wu. Okay, Zehao Wu is a research assistant professor at the University of Macau. He received his all of the bachelor, master, and PhD degree from the University of Macau. He was a visiting scholar and the UCLA in May 2024. Okay, he has been a postdoc researcher at the UM. Currently, he has received a Macau Foundation scholarship and many other scholarships from Macau. His research interests include complex mechanism, energy harvesting, and magnetic robot. Okay, Dr. Wu has published a series of journal papers, including the IEEE ASME transaction mechatronics, IEEE transaction industrial electronics, and so on. Okay, let's welcome Dr. Wu.
Hi.
Yeah, it's okay.
Hello, everyone. I'm Zehao Wu. It is my honor to join this case, and thanks for the opportunity from ICANS. Today, I would like to share my study about the compliance mechanism introduce how it applies in the macro and micro application. Firstly, I would like to have a short introduction to our teams. Our lab is Smart and Micro Nano System Laboratory. We're interested in robotics, mechatronics, and intelligence robot. We research on the robotics system from the meter scale to the nanometer scale, for the mobile robot to the nano positioning stage. If interested on our job, welcome to join our team. Then today, my presentation is classified into 5 parts. The background of the compliance mechanism and its application in constant force polishing, closed environment manipulation, and micro energy harvesting, and a conclusion. At first, what is compliance mechanism? Compliance mechanisms are systems that utilize the elasticity of material which function through the deformation within the elastic regions of material to transmit force and motion. The idea is come from the nature, such as locus lash and cap. And there is a long history for its application. In the ancient times, based on the compliance mechanism, we fabricate the longbow as a weapon, and the dogong is also a kind of compliance mechanism which is helpful to resist the earthquake. Then to now, there are a lot of compliance mechanisms in our daily life, such as the backpack buckle and the 14 fork. And based on it, there are also many amazing applications, such as the subjectal tools, positioning stage, and mice device. Furthermore, it can provide a high precision to the spatial pointing mechanism and as a self-adaptive finger to stably grasping various sets of objectives. Then, as a brief summary, the compliant mechanism has the merit in terms of easy miniaturization, low backlash, frictionless, low cost, and high stability and high compatibility. Therefore, it become a competitively method or solution to improve or solve the problem in many applications. And in this presentation, I would like to share my experiment of using the compliant mechanism to improve or solve the challenge in the application of constant force polishing, closed environment manipulation, and microenergy harvester, which include the application in macro to micro scale. First, I would like to introduce our solution in the problem of constant force polishing. With the development of precision engineering industry, the requirement of high precision machining keep increasing. As the final machining process, the effectiveness, precision of the polishing technology mainly influence the generation of a smooth surface, which has obtained great attention. The polishing technology can be divided into two general working principles, including chemical effect and physical effect. In particular, the most common polishing technology is based on the physical effect. The physical polishing exhibits the benefit of simple mechanism and low cost. Moreover, the polishing and effector can be installed on the robotic arm to achieve high efficiency, high stability, and high flexibility for polishing. Then, how to improve the quality of polishing? Keep a constant contact force on the workpiece is an effective method. Then, the most common solution is the active compliant control. Using a sensor to detect the contact force, then using a actuator to adjust the relative position on the robotic arm to the workpiece. However, a force sensor with a high feedback rate and high precision is very expensive. Moreover, the limited bandwidth also limit the maximum of the feed rate of robot arm and would cause a force overshoot. And to solve the problem of active compliant control, research has proposed a passive compliant control. The most basic idea is connecting a spring between the polishing head and the robotic arm. Then the contact force is controlled by the elastic force of the spring, and its force variation depends on the stiffness of the spring and the displacement variation of the polishing head. And a passive process, the bandwidth of the passive compliant control can be determined as infinity high, then there is no overshoot. And to improve the passive compliant control, our team used the constant force compliant mechanism to replace the common spring. For the constant force mechanism, the basic principle is integrating a positive stiffness and a negative stiffness together. Then we can get a spring that has a region with zero stiffness, which indicate that when in this region, the polishing force is in a constant value. The experimental result verify the effectiveness of our idea with a force variation of 0.6 Newton and no overshoot. However, in this version, there are still many limitations, such as the gravity effect and the constant magnitude cause that this version has limited adaptability, which indicate that a new polishing task require a new constant force mechanism. Therefore, we further update our solution. At first, to avoid large angular momentum, the motion of the polishing head is decoupled and transmit while several guiding elements. Then the performance of the constant force are depend on the negative and positive stiffness mechanism. Since the constant force range depends on its composite negative stiffness range, to achieve a larger displacement of the constant force regions, the curve being chosen to contract the negative stiffness mechanism. And to achieve the adjustable constant force, the position of the fixed end of the positive stiffness mechanism are set as adjustable. Then we can turn the material of the composite force by turning the position of the fixed end of the positive stiffness mechanism. And moreover, the gravity effect is compensated by a counterweight. The gravity effect of the polishing end and the counterweight offset each other. Then the updated version is allowed to work in a operating angle. Therefore, since our constant force material is adjustable and easy increase by increasing the thickness, the main target for designing the constant force mechanism is to minimize the force variation and avoid the material failure. Then, based on the FEA simulation and the genetic algorithm, the structural parameter of our design were optimal turn. And in the simulation, the material of the constant force and force variation in the constant region are shown. And experimental study was carried out to measure the actual performance. Compared with the simulation result, the experimental result of the material and range of the constant force region have both decreased. And it also showed that the measured constant force region with various reloading displacement are inconsistent. The difference may be induced by the manufacturing error, assembly error, and measurement error. Moreover, compared with the previous work, the larger constant region showed that the effectiveness of using the curve being to contract the negative stiffness mechanism. Therefore, with the whole device, we have measured the force region with the force variation less than 1 Newton. And free condition is consistently. With the first two conditions, we can verify the effectiveness of gravity compensation. With the gravity compensation, the force with various operating angle keeps stable, and with different fixed position of the positive stiffness mechanism, the force magnitude can be easily adjusted as expected. Then we apply our device in the position task week, and in this task, we can find that when using our device, the constant force during the position keeps stable and also work as our expect. Furthermore, the force curve during the position task with multiple operating angles are measurement. As a result, verify the effectiveness of the proposed mechanism for polishing under a wide operating angle. Therefore, our design has higher adaptability to more polishing tasks and reduce the economic and time cost. Moreover, the compliant mechanism is also available in the micro application. And in this case, I would like to show you a kind of magnetic bioaxial robot which can be used in closed environment manipulation. In this study, in the micro manipulation, the grasping operation is the basic operation. Therefore, a micro gripper is a typical device in the micro manipulation. And the typical application is the micro manipulation of a single cell. Moreover, in the cellular study, the typical requirement including grasping, rotating, and locomoting. And to avoid potential contamination, the manipulation is preferred to operate in a closed environment. Then in the literature, there are various grippers with different driving approach. And in this project, we set the magnetic actuation as the driving approach as is marine in terms of high compatibility to biological tissue, non-contact feature, high stability, and low trouble of charging. It can achieve many interesting aspects as shown in our other works, such as creating a soft robot with interval moving, balance controllable release, and also in vivo locomotion in the zebrafish. Therefore, magnetic actuation provide a promising solution for manipulation in the closed environment. And in the existing world, the magnetic gripper can be simply classified into two types: magnetic torque-based and magnetic force-based. For the magnetic torque-based gripper, we can rotating the grasping sample by changing the direction of the magnetic field, but also the direction of the grasping and will change together. Then its locomotion commonly achieved by the magnetic gradient or an alternating magnetic field, but both of them has its own defect. Then for the magnetic force-based microgripper, the rotating and locomoting of sample is achieved by two actuation magnet move together or in the opposite direction. But for adapting multiple manipulator with cooperative work to solve various tasks in a closed workspace, the control of the multiple manipulator is complex and difficult. And to improve the tools, our method is designing an integrated bioaxial robot based on the compliant mechanism, which enable a much easier control. First, the mechanism can be determined as three parts for three functions, including grasping part, rotating part, and locomotion part. The grasping part and the rotating part is with the same working principle, which is actuated by the magnetic torque. While the magnetic torque, the tool insert magnet actuates the link to deformation. Then the displacement is amplified by the deform mechanism and guiding to the parallel mechanism. Then the locomoting is realized based on the magnetic force. The locomotion part is moved by following the motion of the outer driving magnet. In addition, the torque or the torque of the locomotion part is zero due to the assigned support arrangement of the inserted magnet. Then the simulation result clear so how the proposed robot grasps and rotating the sample. And the proposed bioaxial robot can easily fabricate by the silicon gel reserve mode. Then the grasping and rotating motion is simply controlled by the input current of the electromagnetic coils in the corresponding direction, and the locomotion of the bioaxial robot is following the motion of the external locating manipulator. And several experimental studies were carried out to measure the actual performance of the prototype. The snapshot demonstrate the effectiveness of our design to grasp and rotating sample in a closed environment. In addition, the dead band denote the minimum driving displacement between the locomotion part and the external manipulator. For a demonstration of our robots, a zebrafish and boy with a diameter of 1 millimeter is manipulated to verify the effectiveness of our robot. And in the figure, the red cycle shows the position of the zebrafish and boy, and the red arrow indicate the labeling direction of the zebrafish and boy. Then the combined mechanism can be also applied in the field of micro energy harvesting. As we know, power supply is a very important part for the use of device, since the traditional energy supply device has the deficiency in terms of low energy density, short working life, high difficulty of replacement. It is non-suitable for the wide distributed sensor in today's society. Therefore, with the development of the energy consumption of the sensors, as a kind of small-scale and high-integration self-sustaining energy supply device, micro-energy harvesting have been paid great attention to. Therefore, we focus on the study of the piezoelectric energy harvester, which can convert mechanical energy into electric energy based on the direct piezoelectric effect. And with the memory of small size, simple structure, and high energy density, since various environment has various situation, to achieve better output energy, the energy harvester is designed to be designed for various dedicated situation. As the energy most near to ourselves, the mechanical energy for human being has attached the attention for the researchers, especially the human working. Then, as the human working footstep has a high output force, the piezoelectric start with a high exchange become the first choice of energy harvesting for the human working footstep. Furthermore, as a energy supply device, the higher energy, the better the performance. Then we use the compliant mechanism-based force amplifier to enlarge the complex force of the ends of the piezoelectric stud. In addition, as a compliant mechanism, the force amplifier is easy integrate and low cost. And as during the human working on the floor, the footstep is done not only the vertical force but also a horizontal friction force in the floor. Then using multiple piezoelectric studs to realize multi-directional energy harvesting is not economic. Therefore, we developed some dual axial or tri-axial energy harvester by only using a single piezoelectric stud. The basic idea is increasing the output energy and reduce the cost. And as the consideration, the value is increasing. The base working piezo can be briefly introduced by using the mechanism such as the level mechanism, conical mechanism, and the couple to change or transmit the input force to the required direction of the force amplifier. And the force amplifier is adapted to enhance the input force of the piezoelectric stud for generating a higher output energy. And there is a mechanism design example of an underflow energy harvester with the dual axial piezoelectric energy harvester. The main mechanical component are the conical mechanism and two-stage force amplifier. And the performance of each part is verified by the experimental study. Measure the average output power, then find the optimal resistance, measure the output voltage, then calculate the force amplification ratio. And the experimental results are summarized. Then a particle application test will conduct. The output energy per working footstep was derived from the average value of 10 tests, which were carried out by 10 people with various weights. First, it is observed that the output energy per working footstep increasing as the increasing of human weight. Then the coefficient value of one working footstep are shown with an applied weight of 62 kilogram. The harvested energy per working footstep can be divided as 7 millijoule. In addition, our device is contributed by a small input reflection, which will not influence the balance of the working people. It is suitable for scavenging energy for the human working. And to conclude this presentation, in this presentation, based on the compliant mechanism, 3 words are introduced, including the passive position and effector with adjustable constant force and while operating angle, and magnetic bioaxial robot with compact structure and easy operation, and a dual axial underflow piezoelectric energy harvester, which show showing that how to use the compliant mechanism to improve or solve the problem in different applications. That's all my presentation. Thank you for your listening.
Okay, thank you, Professor Dr. Wu, okay, for the presentation and for the sharing of the compliant mechanism design. Okay, the next speaker and the last speaker is Professor Ying Jiang. Okay, let me give a brief introduction about the Professor Jiang. Okay, Professor Jiang is the assistant professor and the Department of Electromechanical Engineering at the University of Macau. She received her bachelor's degree in microelectronics from Shenzhen University, master's degree in physics from Tsinghua University, and a PhD degree from Nanyang Technological University in Singapore, under the supervision of Professor Xiaodong Chen. Okay, after the postdoc researcher at the Nanyang Technological University, she then joined Professor Zheng Bao's group at Stanford University in 2023. And then she joined our University of Macau in this year. Professor Jiang's research focused on soft stretchable electronic devices. She had published more than 25 papers on high impact journal, including one paper in Nature and the first author. And her research work has been featured in special report by Nature Research Briefing and numerous prominent media outlets. Okay, let's welcome Professor Jiang.
Thank you very much for your very nice talk. And I'm very happy to be here to share my work with all of you. And today I'm going to talk about the interconnect and assembly in soft bioelectronics. So first of all, let me introduce a little bit about my research group. My research group focuses on the functional soft composite materials and also the conformal bioelectronic interface and also the integrated wearable or implantable soft electronic system. As I just joined the University of Macau this March, so my group will be a new but very innovative one. And we are now hiring the postdoc and PhD. So if any of you have passion in this field with a background of chemistry or material or mechanical engineering or biomedical engineering, you are welcome to join us. Okay, so before we start, let's look a little bit at the background. So why we need the stretchable devices? So actually, we all know that the rigid silicon electronics are developing for so many years and we all benefited from it. But when it comes to interacting with our human tissue, the soft human tissues like our muscles or brain or the heart, there is actually a large mechanical mismatch in between the materials of these two fields. That's why the people in the research field and the industry field, they develop such kind of stretchable electronics. It's essentially required for human-machine interface. And actually, we can divide them into several aspects, like the wearable devices, such as the e-skin, and also the implantable devices, which functions inside our body, and also the biomedical tools, such as the minimally invasive tools. So actually, the stretchable devices, and they serve as a bridge in between the biological world and the digital world, and we need a bidirectional information change. And this is also not only required by the academia, but also required by the industry because there is a growing market on it. And here is my research work in this field. And actually, I took it step by step. So I will introduce them one by one. So first one is the stretchable strain sensor, which is actually my first work in this field. So why we need the stretchable strain sensor is because, like I said before, there's a large mechanical mismatch between the rigid sensor and our human body. But our human body, the mechanical signals are very ubiquitous in many organs like the lungs, the bladders, the heart, the phonation. So if you want to extract these mechanical signals, we may need the stretchable string sensors in a soft form. So in the previous years, there are challenges in this field, but the biggest challenge at that time is the low sensitivity, which means that the gauge factor of it is lower than 50, and as well as the large stretchability and also the cyclic durability. So what we did is that we developed a kind of aesthetic mechanical metamaterial. So what is metamaterial is that instead of the natural material, the aesthetic metamaterial has a negative Poisson's ratio. So we know that in the nature, the incompressible materials such as the TPU or the PDMS, they have a Poisson's ratio of like 0.49, which means if you stretch it in one direction, then in the other transverse direction, it will shrink. But if we use the aesthetic mechanical metamaterial with the negative Poisson's ratio, that means you can get a two-directional increase in length under the mechanical deformation, and this will benefit in the stretchable strength sensor and increase its sensitivity. That's the gauge factor, and which is also confirmed by our experimental study and also the finite element analysis. So previously, we developed the aesthetic design for the stretchable string sensor. Then that is a specific strategy of one kind of sensor. So then we think, why don't we extract some kind of universal strategy for the stretchable mechanical sensor design? So here is our result that we find that we can employ the strategy of heterogeneous string regulation, which is in contrast to the homogeneous string distribution. We can develop different types of metal structure in all materials and make the string regulation distribution to distribute wherever we like, so that we can easily enhance the sensitivity of the stretchable mechanical sensor, and that would be a universal strategy. And in the previous two work, we focused on the stretchable string sensor, and that is one component of the whole stretchable device. So during the practical application of the sensor, we find there are many challenges in this field, and one of the biggest challenge, the biggest bottleneck, is the interconnect and the assembly of the stretchable devices. So we may take a look at this roadmap of the stretchable electronics. We can divide them into 4 stages. So the first stage is the silicon-based microelectronics. It is actually where we are staying at now. It consists of the rigid chip, PCB, sensor, and power. And then when it goes to the stage 4, which is the all stretchable electronics, we will find that all the components are already made to be stretchable. But actually, this stage, many research groups are putting efforts towards it, but because the silicon-based chip, they consist millions of transistors working together, which is a very challenging one. So what I do believe is that currently and for a long time, our field in the stretchable electronics will stay in the stretchable hybrid electronics, which means we have components such as chips and PCB, power sensor with different mechanical properties. And we need to assemble them together to make a functional system. So what people do Now, the current bonding techniques for this, to assemble this kind of different mechanical components, we use the commercial anisotropic conductive film, that is ACF film, and we also use the conductive paste, silver, copper, or gold. And when it comes to the PI-PCB, we can also use the solder to connect them. But the problem here is that such current bonding techniques, they have a high signal noise from the connection region, which results from its low electrical stretchability, which is lower than 50%. And also there is a very easy debonding failure, which means the mechanical stretchability of such kind of bonding is not very good. So this situation is a little like the Kennecke law, which means the robustness of the whole system depends on its weakest part. So no matter we have how strong, how robust one component is, such as, for example, if I have a sensor that can be stretched to 1000%, but if the interconnect part in the system is very, very big, then the whole system, it cannot have a very high robustness. So there are a few research attempts trying to solve this kind of challenge. The first one is the all-soft electronics, which eliminate the soft and rigid interface altogether because they don't use chip on the other silicon-based components at all. And actually, it's a very smart method. But if we want to get a more complex circuit design and more complex function, the silicon-based electronics may still be needed. And also, there are many works developed the liquid metal or self-healing material and conductive material composite or mixture. But they both have their drawbacks like low mechanical adhesion or large thickness. And there is also some work that developed the stretchable paste, like this one is the stretchable ACF one. So this one is actually a very interesting work. It developed a freestanding stretchable ACF, and which is applicable for different modules. And all these kind of strategies, they have their advantages, but also have some drawbacks. So we still need a more general, a more effective and reliable method for interconnect and assembly of the stretchable electronics. So what we designed is that we developed a strategy for this to solve this challenge. We developed such kind of biphasic nano-dispersed interface, what we call the bind interface. So it looks like a pure metal thin film on the polymer, but if you zoom into it, you will find that actually there is a nanoscale interpenetrating nanostructure in between the polymer, in this case is SEBS, and the metal nanoparticles in between them. So it can effectively bond both between the three elementary types of the components, the rigid one, the soft one, and the encapsulation one, because in this kind of interface, there are both exposed polymer, self-healing polymer, and also exposed metal nanoparticles on it. And also it is free of paste, and it has a more robustness function than the conventional paste-based connections. So why the elimination of paste is good for us, we can take a look at this kind of finite element analysis. In the left case is the conventional interconnect with a rigid paste, and the rigid paste will result in the high concentrated stress in the interconnect region. But in our bind interconnect configuration, we don't have the paste. We just have two interfaces and press them together without paste. So this will reduce the concentrated stress in this kind of interconnect region. So this is kind of the experimental performance of our bind connection, and we compared our connection to the commercial paste, ACF, copper, carbon, silver, and we find that we increased the mechanical stretchability a lot from the conventional 60% to larger than 600% in our case, and also the electrical stretchability from 45% to larger than 180%. And also remember that not only the soft materials, also we need to bond the soft module together with the flexible module, like in this figure. So we also tested how this kind of bind connection behave in case of the soft and the rigid module connection. So we find that also it's very good, better than the conventional paste-based the connection, and also our kind of the bind connection can be applied to different materials, including the PI, the PT, the glass, or the metal. So it is actually a universal strategy for the rigid or flexible module connection. And finally, there is another type of the components in the stretchable electronics, that is the encapsulation component, which means that the encapsulation provides mechanical protection and electrical insulation. So in this case, like here, we have the bind encapsulation on top of another type of bind interface, and we find that such kind of bind interface have a larger stability and a larger adhesion than the conventional part. And then we did some characterization work to find the experimental performance is good, but why is it? What happens in the nanoscale? So we find that in the nanoscale, actually, there is an interpenetrating nano network in between the polymer and also the metal microstructure. So if here in the middle is the bind interface, which achieve a balance in between the metal and polymer. But if we increase the polymer ratio, then we will get a very adhesive but non-conductive interface. And if we increase the metal volume, we will find that the interface is very conductive, but it is not adhesive at all. So actually, our bind connection is a balance in between. And also, we want to know that why it happens and what is the basic mechanism during the fabrication of such kind of nanoscale interpenetration. So we did some experimental and simulation work and find that during our thermal evaporation of the metal nanogold film, we find that the experimental temperature actually increased to over 90 degrees C, which means that our polymer substrate undergoes some kind of glass transition, and the whole polymer becomes softer. And here is the simulation. Here is the simulation which illustrates how the gold atoms interpenetrate into the polymer during our fabrication. And this is the side view, and then this is the top view, and this is in cooperation with Dr. Guijin Zhou and Prof. Gao Huajian for the molecular dynamics simulation. So actually, we will find that in 20 nanoseconds in the case of the impinging gold atoms, the gold atoms actually forms from the interpenetrating to the nucleation growth. And then after the first few tens of nanoseconds to an experimental of 1,000 or hundreds of seconds, the nucleation grows, and then the nucleations of the micro nanoparticles make them contact with each other and then merge and then make a continuous conductive pathway. So this simulation result is also consistent with our experimental result, which shows there is actually an interpenetration network, and also both the polymer and the metal nanoparticle is continuous. So after we get the mechanism and underlying mechanism of this kind of interpenetrating bind interface, then we are wondering how we can use this kind of interface as a connection and assembly strategy to increase the performance of the whole stretchable device. So this is the first device configuration we tested. There are actually 4 modules of different types, including the encapsulation, the ultra-thin module, and the thick, robust wiring module. And actually, we use this kind of ultra-thin electrode to wrap around the tissue inside. This is a rat body, the rat muscle. And then by folding over this kind of ultra-thin electrode, we can achieve a suture-free and self-adhesion configuration of the device. But the unique property of this device is that the electrode part of this device is ultra-thin, but the wiring part here is very thick. So it means that we can combine these two kind of strategy, the ultra-thin electrode for a conformal contact with the tissue. In this case, is a muscle, and the robust thick wiring provide a robust noise-free or minimal noise wiring. So then, compared with the thick configuration or the ultra-thin configuration, we find that in the configuration using 2 modules with our bind interconnect has a very good signal-to-noise ratio, which means we have a clearer signal from our human body, in this case, from the rat. And also, this kind of bind electrode is suitable for different sized organs, so including the muscles in previous slide, and also the neuron, the sciatic nerve, and also the bladder. Here's the bladder stimulation result, and also the ECOG, which means we put this kind of device onto the cortex of the rat and tested the difference between the signals from healthy and epilepsy rats. So all these signals suggested that we improved this kind of implantable bioelectronic device performance by using our bind connection and assembly strategy. And also, for a more complex device, we fabricated an on-skin 21-channel EMG device, which is the configuration is like this. It has a 5 module, including the rigid one, the soft module, and the encapsulation module. And also, we find that there are many 3 types of bind connection in this device, but together they work very well. And actually, if we use the conventional commercial ACF connecting in this kind of configuration, and when we press the region of the interconnect, we will find that when we press and release, there is a large noise of it. But if we use our bind interconnect, we'll find that during the pressing and releasing stage, the noise is very small, which means we have a clean and low signal-to-noise ratio. And so a little summary of this work is that we developed this kind of biphasic nano-dispersed bind interface as a connection and assembly strategy for the stretchable devices. It is free of paste and very fast and easy to use. And actually, we believe it opens a new paradigm for the assembly of the stretchable hybrid electronics. But this is still the first version of our connection strategy. So what is still needed there are reusability or maybe the stimuli triggered connection, because sometimes you don't want to use pressure to trigger it. You want other stimuli like the height or heat to trigger the interconnects. And also there are some conductivity problems, not only for this kind of bind interconnect, but also for the whole stretchable electronics field. So lastly, I'd like to thank my master supervisor, Prof. Wang Jiaping from Tsinghua University, my postdoc and PhD supervisor, Professor Chen Xiaodong from Nanyang Technological University, and also my postdoc supervisor, Prof. Zhao from the Stanford University. And also I got a lot of help from my collaborators, including Prof. Gao Huajian, Liu Zhiyuan, Li Guanglin, Naji Machihisa, Boli Bird, Marcus Antonietti, Slumu, and many my colleagues and friends. Yeah, that's all of my presentation. Thank you all for listening.
Okay, thank you, Professor Jiang, for the nice presentation. The next is the Q&A section. In the discussion section, okay, first let me introduce the panelist. Panelist is Professor Jinrong Liu. Okay, he is assistant professor in the Department of Electromechanical Engineering at our University of Macau. Okay.
Okay, thank you, Professor Xu. Yeah, I'm Liu Jiang from the Department of Electromechanical Engineering, University of Macau, and my background is from the robotics and control. So if you have interest in the robotics and controls, and I'm recruiting PhD students as well, you can reach out to me and find my email address from the website of our department. Okay, so thank you very much to the speakers. So for Professor Lei, okay, so thank you very much for your very nice presentation on the topics of the embedded 3D printing of soft materials. So I have a few questions for you, and so my first question is on like slide 20. Could you share your screen to us?
Okay. Yep. So
Okay, could you turn to the slide 20?
yeah. Okay.
Slide 20?
Yes.
Okay, and I noted that you utilized a sacrificial material for fabricating the Cochlear model. And what is the use of the sacrificial materials here?
Okay, yeah. So thank you for the questions. So sacrificial materials is actually a general name about the ink that is able to create hollow cavities inside a matrix. So there are many different types of sacrificial ink available. So there could be sacrificial ink could be a gelatin ink or aqueous hydrogels. And in this particular work, I use a materials called Plutonic F127 as the sacrificial materials. And so these materials has a very good printability. So this is the reason why we choose these sacrificial materials. And so the special properties about these sacrificial materials is that Plutonic F127 has a high viscosity when we heat these materials up. So during printing, we actually heat the ink up, and then such that the sacrificial ink can maintain the structures inside the matrix. And when we want to remove these sacrificial materials, we can cool it down to 4 degrees Celsius, and then these sacrificial materials will be liquefied such that we can easily flush away the materials out. Yeah. So sacrificial materials is an ink utilized for making the hollow structures inside a construct.
Okay. And my second question is, why the color of the HPC materials, as you show in your slide 21?
Oh, yeah.
Slide 21?
Oh, yeah, I think it should be this one. Yeah.
Okay, this one, yes. Also, why the color of the HPC materials can be changed by concentrations and temperatures? Could you explain the principles behind this?
So, this is thank you. So this is a very great question. So so the hazardous supercellulose, I think it is a very interesting material. So as I have previously mentioned, at a specific range of concentrations, this polymer can self-assembly into a helicoidal nanoarchitectures because of this. Because of the intermolecular interactions causing the polymer to arrange in a helicoidal nanoarchitecture. And so, so these helicoidal nanoarchitectures will have this kind of features, and then the pitch distance of these helicoidal structures will determine the wavelength of the light reflecting from these structures. So if we increase the concentrations of the hazardous supercellulose in the solutions, the pitch distance will decrease, so therefore causing a shorter wavelength of light to be reflected from the solution. And so you can see that, so if we increase the concentration from around 61% here to 70%, the color actually will change from red to purples. And so this is due to the decrease in the pitch distance. And so temperatures will also have a similar effect. So if we increase the temperatures, the pitch distance will increase. So therefore, the color will shift to a more red color.
Okay. Yeah. And could you turn to the slide 5?
Yeah. Okay. Yes.
Yes. And okay, what is the resolution of 3D printing techniques you mentioned here? What is the resolution?
Oh, okay. So the resolutions of the 3D printing technique utilized here. So for direct ink writing, the resolutions is around 100 micron. So it also depending on the types of materials and the cross-linking mechanism. But I think the best resolutions we can obtain with the direct ink writing is typically around 100 micron. And for digital light processing printing, it could achieve I think 50 micron is achievable, but it really depends on the materials we would like to print, and as well as the cross-linking mechanism.
Okay, for the embedded printing soft materials on the you show us on slide 12.
Yes.
So what are the major difficulties for the embedded printing soft materials here?
So I think so compared to normal traditional 3D printing, so normal in-air printing, because in normal in-air printing, there is only one phase involved during the printing. But in embedded 3D printing, there are actually 2 phases involved in the printing process, the ink phase as well as the bath phase. So we need to match the properties between the ink and the bath. So the key difficulty is that we need to find a supportive bath that can correctly match the properties of that can be compatible with the ink materials. For example, so we need to match the chemicals properties, interfacial properties, rheological properties, etc. And then at the same time here, after we point out, at the same time, the supportive valve also need to be compatible with the cross-linking mechanism of the ink. So I think the key difficulty is to find a supportive valve that can actually correctly, or that is compatible with the properties of the ink, as well as compatible with the cross-linking mechanism of the ink. Yeah, so because there are actually many types of hydrogel materials. So I personally think that it will be beneficial if there is some kind of guideline or standard to tell the user how to what is the correct supportive valve for embedded printing the hydrogel materials. So I personally think that this guideline will be very useful for the user to efficiently use these technologies. Yeah, so the key difficulty, to answer your questions, the key difficulty is to find a supportive valve that can that is compatible with the ink properties as well as the cross-linking mechanism of the ink. Yeah, so thank you.
Thank you very much for your answers. I have no more questions.
Can I ask a question? Since probably already mentioned the supported valve. So I'm just out of interest. What are the commonly used materials for the supported valve?
So you can see my screen, right? So so these are actually the commonly used supportive valve used in literature. So the gelatin slurry and the aqueous fluid gels. So these two materials are based on natural hydrogel materials. So these supportive valves are more commonly used to print biological hydrogels such as collagens and extracellular matrix protein-based hydrogel materials. And for this carbopool, it is a synthetic modified polyacrylic acid. So the carbopool is also a hydrogel commonly found in the skincare product. So it is a very transparent hydrogel materials. But so this is a synthetic material, so it might not have a good. The biocompatibilities may not be as good as the gelatin slurry and the aqueous fluid gel. And so these are for printing hydrogel materials. And if we want to print elastomeric materials, we commonly will use oil-based supportive valve materials, such as minerals oil-based supportive valve or the silicone oil-based supportive valve materials.
Thank you very much.
Okay. Okay, perfectly. Okay, following the question from the panelist from other professor, I have one question. Okay, because today's topic is the flexure for robotics, right? And like to know whether, okay, for example, if I design a robot in any shape, can it be fabricated by the 3D printing for the hydrogel material?
Yeah, so I think it is possible to fabricate the soft robot with the embedded 3D printing method. So for examples, the pneumatic soft robot that have many channels inside. So this is a hollow structures. So embedded 3D printing can be utilized to print this kind of hollow structures. And then there has been some work available as well about using embedded 3D printing to produce natural alginate-based soft robot that can be driven by the pneumatic mechanism.
Okay, very good, very good. Okay, because there are many soft robots and they're not easy to fabricate. But with your method, I think we can fabricate more robot, right?
So
different shape.
Yeah, so I think 3D printing is a very good method because you can also customize your design very easily.
Yeah. Okay. Very good. Okay. Any other question for other speakers?
So, Zehao, Dr. Zehao. Thank you very much for your
I-
presentations on topic of compliant mechanisms and its applications. So I'm a bit more interested in the micro polishing task you develop, passive polishing and effective. Okay.
Yeah.
So could you share your screen to us? And yeah, for
Which
the
slide?
like slide 9. Yes, and you have developed a passive polishing and effective, right? Here.
Yes.
So why do you choose the passive polishing and effective rather than the active polishing effective?
As this slide shows, we can know the base working principle of the active comply control. And this control, which is based on the sensor and actuator. And at first, the sensor is to detect the force signal between the polishing head and work pins. And if we want a pretty good result for the control, we need a sensor which is with a high feedback rate and high precisions. And that kind of force sensor is very expensive. And also, for the active actuator, its bandwidth is always limited. And for the limited bandwidth, which will cause our robotic arm can only work in a low feed rate. Otherwise, when we fast changing surface, if we move in a high feed rate for the robotic arm, then the actuator cannot follow the action. Then the force variation will be very large.
Okay. Okay. Thank you. And could you turn to slide 10, the next page? The next slide. Yes. This is the one you have proposed, right?
Yes.
And why do you call it constant force here? What does the constant mean?
The constant force, we can considering our mechanism as a spring, but this spring is very special. This spring is parallel connect by two spring. One is with the in this curve the positive stiffness, and another is with the negative stiffness. And then when we compose the positive stiffness together and negative stiffness together, we get a region which has the zero stiffness, as shown in there. And when we have a zero stiffness regions, it indicates that in this region, no matter the deformation, how to change, the force is keep maintained in a constant value. Then it is then in with this constant value, then if we keep our robotic arm, the polishing head and the workpiece in this region, then the contact force will in the constant value. Then we can find in this figure the force variation is less than 0.6 Newton. Yes.
Okay, it is a adjustable constant force, right?
Yes.
And how do you address it?
We can find that in this figure, we can find that in this works, our constant region is within about 1 millimeter, and the precision of robotic arm is also within this range, and which we can determine that we can easily keep out the position head and the workplace in relative position within our constant region. Then the contact force will be in our determinant force.
Okay, thank you very much for your answers. I have no more questions.
Oh, so yeah, so can
go
I
ahead.
ask questions? So I also have two questions to ask Professor or Dr. Wu. And so I think you mentioned the gravity compensations to achieve constant force polishing.
Yes.
Yeah. So why? So I'm curious about why these gravity compensations is needed. So if you don't do these gravity compensations, so what will happen? So will this limit the performance of the devices?
Thanks for the question. It is a very good question. As this figure, beta denote the operating angles, and then when we are without the gravity compensation, as our position head has a mass, and then when we turn this angle, which means that the gravity force in the position head is also changed, and then our constant force value will change with the change of the operating angle, and then it cannot call a constant force position because the force magnitude is changed. But when with the gravity compensation, we all within our working angles, our force magnitude is kept in a constant value. Then it can be used in the polish path with the continuing change angles, such as in this slide, that there are polishing task with a continuous change angle, and our polishing force is within our is in our exact. Can you?
Yeah. So if you don't do this kind of gravity compensation, how much will is there any parameters to quantify the performance, and how much will this affect the quantitative performance?
It is based on how heavy our polishing head is. The more the more heavy the polishing has, the effect cause much influence on the polishing.
Yeah. Okay. Thank you. So for my second question, so I in your videos, so I saw that your gripper can be manipulating a zebrafish embryo. So I think this is very amazing. So I'm wondering, what is the size of the zebrafish embryo, and how do you control the contact force of the gripper such that the force of the gripper will not damage the silverfish embryo? Because I think the silverfish embryo should be very soft and fragile. So how do you actually control the contact force such that the force of the gripper will not damage the embryo?
Thank you for your question. Is in this size, our gripper is grasping the embryo and locomoting and rotating it. How we adjust the contact force of the embryo, we can, as our experience, the molecule of the zebrafish embryo is in a constant way, and we can easily know that in what deformation the zebrafish embryo will not be damaged, and then we can get this information in the image camera. Yes.
Okay. Oh, thank you. So I don't have further questions.
Okay. Thank you, Professor Lee. Yeah.
Hi,
Please go
Dr.
ahead.
Wu.
Yeah.
I just have one question about the constant force polishing. And actually, the polishing head and the sensor feedback, currently the relationship is 1-to-1, right? One head and one feedback. So can you give some comments on what happens if we have more than one polishing head?
For the with the polishing task with one more police head.
Yeah, maybe you need to apply your polishing head to some curvature environment or the environment with different mechanical properties.
Okay. It's a good question. For the previous work of our team, as our constant force material cannot be changed. So when we different polishing tasks, we need to redesign and reassemble a different constant force mechanism. And so we update our version that we call that adjustable constant force. And then when we adjust the preloading displacement of the fixed end of the positive stiffness mechanism, the force displacement curve of the positive stiffness mechanism will shift, and then the material can be adjusted so that with different polishing tasks require different polishing force, we can just adjust our piloting displacement so that we can obtain our expect polishing force.
Okay, thank you very much. I have no more question.
Okay. Thank you, Professor Jiang.
Okay. For the third speaker
continue.
is Professor
Yeah.
Jiang. Thank you very much for the presentation on the topic of soft bioelectronics. So I have a few questions for you. So the first one is, in your previous work, you developed a unique nanostructure, the bind interface as a soft connections to assemble the stretchable electronics together. And this connection is very robust, right? And it can enlarge mechanical strain. So what do you think is the connection failure mechanisms here?
Okay. So actually, we have different types of failure in this case. So both the electrical failure and the mechanical failure. So the electrical failure means that the surface of the bind interface have long propagating microcracks that is so long that it hinders the electron pathway, so that it hinders the electrical conductivity. So which means that at 50% in case of the commercial connection, or the 180% in our bind connection case, the electrical failure will happen, and the microcrack will be propagated to stop the electron pathway. And this is the first type of failure. And the second type of failure is the mechanical failure, means that the connection of these two modules are totally deformed and be torn apart, and then the connection like this, it won't be held together. It even if you release the mechanical deformation string, it cannot be saved. And because I think in the traditional field, there are several modes of the failure, like the cohesive failure, the adhesive failure, the substrate failure, and the most of this failure depends on where the failure takes place. But in our case, because this one is a special case, a special connection, because we don't use the conductive paste, it's free of paste. We just use two interfaces connecting them with each other without any paste. So that means our failure model can fall in either the cohesive failure or mechanical failure. And I hope that answers your question.
Okay, so after the connection fails under large deformations, do you think it can recover or be reused? Or we will have to use another connection interface instead of reusing the old one?
Yeah, I think for the mechanical failure, it cannot be recovered. And actually, as the picture shown, it actually falls into two parts. But one way to circumvent this problem is that we can prefabricate a longer connection. And when this part of the connection fails, then we can cut it and use the other preserved part of the connection. But there's still it didn't solve the challenge of the reusability. Actually, I talked a little bit about the reusability here, which means that if we want a Lego-like assembly of the stretchable hybrid devices, that we may need the reusability. So it can enhance the ease of use and tolerate the assembly faults, especially when after we use that, we can disassemble it, then use the module to another system. Yeah, I think that's a promising future. This version of bind connection cannot achieve this kind of function, but I believe there are some ways to achieve that in our future work.
Okay, very good. My third question is, it seems that you can make your soft connection with many channels. So what is the spatial resolution of your connections, and what is the current level of commercial paste?
Oh, on the resolution of the channel, actually we can see here the device here is this one. The device here is an on-skin 21 channel EMG device, means that it has a 21 channel, and actually we can shrink the dimension of this kind of connection down to 100 micrometer, that is 100 micrometer gap and 100 micrometer channel. And this actually is enough for connection to the rigid commercially available PI PCB, because the fabrication technique of PI PCB